Neural networks are probably one of the most exciting machine learning algorithms out there, as they can accomplish feats that other machine learning algorithms simply cannot do. But what is it that makes neural networks so powerful? To answer that question, we'll talk about three things: how biological neurons work, how neural networks develop over time, and how perceptrons work. Humans can do incredibly complex tasks, like drive cars, make music, and solve math equations. So it's quite natural that we would like to try to create an intelligent machine that mimics the functionalities from that of a human. So what is responsible for controlling the actions of humans? Well, that will be the brain, and the brain is composed of billions of neurons, all connected in an incredibly complex web of interactions. Each neuron in our brain receives short electrical impulses, called signals, from other neurons via the terminals. When a neuron receives a sufficient number of signals from other neurons, it fires its own signals. Even though individual neurons behave in a simple manner, the interactions of the neurons is responsible for operations of a complex task. As you can imagine, we want to build a simple artificial neuron to replicate how the biological neuron works, and then let the interactions of the artificial neurons be responsible for building intelligent machines. Let's take a look to see how the idea of artificial neural networks develop over time. With the inspiration from biological neurons, McCulloch and Pitts invented the first artificial neural network at the University of Chicago in 1943, where they presented a simplified computational model of how biological neurons work together. However, from 1943 to the early 2000s, neural networks entered the dark ages, where very few researchers pursued the idea, and funding for that research was very low. Those who did work on neural networks, like Yoshio Bengio, were actually ridiculed by the scientific community. The main reason why there was so little support was that other machine learning techniques offer better results and had stronger theoretical foundations. However, a few things changed in the early 2000s that led to a dramatic shift in the frontiers of machine learning. First, because of the internet, there is now a huge quantity of data. It turns out that when there is a lot of data and a problem is complex, neural networks outperform all other methods. Second, there was a huge boom in computing power since the 1990s, as technology has gotten better and more specialized. For example, Moore's law continued to stand its ground, while specialized hardware like GPUs made training neural networks computationally feasible. Third, there has been major improvements to the training algorithms, and researchers have empirically shown that neural networks have significantly outperformed other machine learning techniques for tasks such as ImageNet in 2012. And lastly, once the ball was rolling and success was apparent, research on neural networks have received a ton of funding. Many intelligent researchers decided to pursue neural networks, and more successful neural networks are shown and more funding is given. Now let's talk about the artificial neural network architecture, the perceptron, that continues to be relevant today. Let's consider the perceptron architecture with only a single neuron. That neuron is associated with n many different weights, where n is equal to the number of input features. Inputs to the perceptrons are the feature values. We first compute a weighted sum of the input values and the weights, and then add a constant value called the bias. Next, we apply an activation function to the weighted sum and then return the output. As you can kind of see, this architecture mimics how the biological neuron behaves. Our artificial neuron takes in signals from our inputs and then sends a signal out. Now, what happens when we have more multiple neurons in our perceptron. The basic idea is the same. Each A1, A2, AK is a neuron that's shown in the previous slide, and each different neuron has a different set of weights associated with it. If we have K neurons and N input features, then we would have K times N many different weights. When using a perceptron, we pass the features to each of these neurons. So for each neuron, say A2, it computes the weighted sum of the inputs features x1 to xn with the weights corresponding to that neuron. Then each of our neurons will produce an output which we can feed into something else. Now let's consider the case where we have multiple layers. The first layer is going to be what we described in the previous slide. Each layer after the first layer takes in the output of the previous layers as inputs. We can then stack as many layers as we want, but we always have a final layer that can be used to make predictions. To summarize, we described the motivations of neural networks and why it has become so powerful recently. We've also briefly described the architecture of the perceptron. It would be great to try to answer some of these conceptual questions.